Okay, so this is the continuation of page 31. This is the third exercise. This is the continuation, okay? And if you don't remember what the exercise is, that is the exercise that we have been doing, okay? We're going to inscribe 3 polygons inside this circumference, the same circumference, and we saw that if we just take L1, L2, and L3, it's impossible to make them as an AP sequence. It's impossible. Now we're going to propose how can we change a little bit this problem so L1, L2, and L3, they do become an AP sequence. And for that, okay, let me write in this way. I'm going to write in here with this pen in here. So this is the second part, okay? What can we propose to solve this problem? Now, to work, okay, with a solution, with a possible AP sequence, we must add a constant. That is the answer to the problem. A constant to at least one term. Of course, just add one constant. If you add 2, you might get in trouble, okay? Just 2, 1, okay? And this is the most beautiful part of this problem. Let's even put in red, okay? Now, any constant of course, non-zero constant, okay? Any constant will make three non-linear terms become linear. Okay, this is the beauty of the exercise, and that's why I made a separate exercise because actually now we have 3 things that are not linear, and we're going to make them linear. And of course, let's go again to charts. In here, that's what we have. For instance, we have like this here, here, and this one is not linear, okay? See, this it is, oops, it reflects, right? Okay, what I'm telling you is this: if you just try to make those 2 linear, like this, in here, where is the green one? In here. Let's make those linear, okay? This is not linear, and why is not? Well, because to be linear, it would have to be in here, right? This is. What should we do to this number? We have to add a constant. So to bring these points up to here, if we add these constants, we can put that term back into the linear position, and that is going to be linear again, okay? And that is how it works, okay? So, and you can do with any one of them. Let's again put everything here. So this could be another and another one in here. And that is the beauty of math, right? Because things can be very easily solved sometimes, and very okay. So we have those 2, and we have this one, right? Okay, and we have those 2 and this one, okay? The same points. Let's suppose that those are the points that we have, okay? Now, in here, suppose that we had made this line as our default line, it would not change anything. Why? Because if we had done that, all we had to make it is a negative constant and bring this point down. This would be a negative constant, and we can replace that term back just by adding a constant. In this case negative, in this case would be a positive one, right? Okay, and said okay, but if I do this now, it's not possible. It is. Let's suppose that we choose those two terms in here. So we just have to add a constant in here. Add a constant. So you see, and then we can correct this term and put it back in the linear form. So whatever, any constant that we add to any term is going to make that sequence of three terms be a linear one. Okay? So what we are going to do is this. Let's add a constant in the hexagon polygon, right? Sides. I could do in any one, okay? Imagine this is triangle, okay? I could put the constant in any polygon, but I choose to put on the hexagon, okay? And why? Because hexagon has the most simple sides. But anyway, it doesn't change. Okay? Now, instead of, and do you remember, where is it? It's in here. Do you remember? Let me put it here. Instead of L3 equals R, okay, instead of L3 equals R, it will now be what? L3 equals R plus a constant, right? Okay? We are adding now this constant in here. And let's make even this. Okay? We're just adding a constant now. And now what are going to be our lengths? Okay, you used to be, we are not going to change L1 and L2, only L3, okay? I'm just going to copy now the previous answer. Now, returning to our problem, like this. So now our sequence, it is going to be like this. Our sequence will be like this. L1, it is going to be R square root of 3. L2, it is going to be, this is a square, right? Square root of 2. And the hexagon is going to be R plus C. Okay? And now, if this is an AP sequence, remember? So, the middle term must be the average of those two. So, L2 must be L1 plus L3 divided by 2. Agree? That's reason behind all this. So, let's just place it, everything. So, L2 is going to be R square root of 2 must be R square root of 3 plus R plus our beautiful constant divided by 2, of course. Well, in the end, now cross multiplication, 2R square root of 2, it is going to be R square root of 3 plus r plus c. Okay, I'm going to put every term of r is going to the left, and I'm going to put r between evidence. This is going to be 2 square root of 2 minus the square root of 3 minus 1 equals c, our constant. Okay, well, I forgot, I'm writing the constants with red one, right? Sorry. Okay, now, so our constant, because we did all that so we could find a constant. Okay, so our constant, it is going to be exactly this. Oh, it's already in here. So this is going to be our constant. We have finally found our constant, right? Okay, now let's substitute. Okay, because remember that we have this, we have this. I'm just using the same colors. This was the hexagon, this was the square, and this was the triangle. Okay, now I'm just going to substitute that constant in here. Okay, now that constant, it is coming here now. Let's make, I'm going to make at the same time, I'm going to put the constant in here, and I'm going to use again that relation. Okay, that L2 is going to be L1 plus L3, the average. Okay, but now L3 will have this constant. Well, again, this is going to be r square root of 2 equals L1 r square root of 3 plus, what is L3? It is going to be r plus the constant, right? Okay, so it's going to be this. I'm going to put L3. It's going to be r plus r 2 square root of 2 minus square root of 3 minus 1, and everything divided by 2. Cross multiplication, 2 square root of 2, it is going to be r square root of 3 plus, now look what I'm going to do. I'm going to put r in evidence, and this is going to be 1 plus 2 square root of 2 minus square root of 3 minus 1. This 1 goes with this 1, and I'm going to put everything, okay, to the right. Oh, this is an r, right? There is an r in here. Okay, so everything to the right, and the r in evidence. 2 square root of 2 minus square root of 3 minus 2 square root of 2 plus square root of 3. Okay, that's it. Equals to 0. Now, square root of 3, cancel. Cancel. Okay, now look how beautiful it is. This is 0 for sure. So r times 0, it's 0. This means that this beautifully shows to us that r can be anything in here. The radius of our circumscribed circumference can be any number. So for any number that you choose, meaning for any radius that you choose, we are going to have a perfect AP sequence. But now we have to use r square root of 3, r square root of 2, and r plus this one, okay? And just to prove to you that it really works, and this is the last part, I just hope I can put everything here, just to prove to you that it actually does work. So let's put in black, okay? Change a little bit the colors in here. Now L1, let's make, okay, L1 is going to be r square root of 3, okay, and the r is going to be 1. We have to decide because we can place any r in here. Let's make r equals 1, okay? If r equals 1, it means that L1 it is going to be square root of 3. Okay? Now, L2 it is going to be r square root of 2, which is for r equals 1, that is our radius, is going, L2 is going to be square root of 2. And what is going to be L3? Well, L3, let's make something here. Okay, what is going to be L3? L3 it is going to be like this: r plus r square root of 2 minus square root of 3 minus 1. Okay, so in the end it's going to be what? R 1 plus 2 square root of 2 minus square root of 3 minus 1. That, okay, I just wanted to show you that in the end L3 it is going to be this: r 2 square root of 2 minus square root of 3. Okay, this is going to be L3. After we just place a constant, we're just doing this, right? We're just taking a constant and adding like this. Okay, so L3 it is going to be what? R 2 square root of 2 minus square root of 3. For r equals 1, it means that L3 it is going to be what? 2 square root of 2 minus square root of 3. And I have calculated, okay, what are those, okay? Let's put them now in decimals. So square root of 3 it is 1.732. Square root of 2 it is 1.41, right? But let me just 2 to the half, 1.414. 414. And L3 it is going to be 2 square root of 2 minus square root of 3, and this is 1.096. Okay, and if you just make the difference between those, what do we get? I'm just doing the math in here. 732 minus 414. Okay, this is 318. It better be these, right? Okay, so 441 minus 0.96 minus 96. Okay, yes, it is true. And this is going to be the common difference. Okay, so it is indeed an arithmetic progression sequence. Okay, all we had to do is this: we just had to add these constants in here. Okay, I mean adding the constant. It used to be just r, and now it is, we have to multiply by this constant, right? It's just adding a constant, right? Okay, and so this is a positive constant, so the side, okay, the hexagon side was too small, so we had to add, in this case, a constant to make the hexagon a little bit bigger. Okay, we had to increase a little bit the size of the hexagon, and then it would reach this linear, okay, this linear sequence, and now it's everything good. Okay, of course it's not easy, but at least we have discussed it a lot. Thank you very much.